Okay, folks. So we just got done with a lecture about um, just using Newtonian mechanics and having a spherical overdensity in a static spacetime and seeing what happens as this overdensity starts to collapse. What are the dynamics and what is the time scale over which that occurs? And well, what we found was, there's a sort of there's a time scale that's set by Newton's constant, big G, and the density of the material. And what we found was that all kinds of stuff has a collapsing time scale, even the air in this room or water in a pool. And what we found was that apparently structures should just collapse. And so why don't they? Why doesn't the air in this room collapse, for example? And of course, the answer to that is pressure. And what I thought I would do is go beyond the sort of hand-wavy derivation that Ryden gives in the book and actually go through a little bit of fluid mechanics, which may be a little bit beyond the level that you're at, but that's okay. I would advocate that you mostly spend this video just trying to pay attention and follow along, see what math you can pick up. But I wouldn't worry about trying to take detailed notes and trying to understand every factor of Laplacian, etc., and just try to get a sense for where this wave equation comes from, as we'll see. And then I'll give a follow-up video which will add some more physics on top of it. Okay, so what are the ingredients here? So first of all, we have Newton's second law, which is great. We're going to use Newton's second law in a non-curved space-time, should be great. And so anyway, what that looks like is ma is equal to F net. And so I'm going to write that as acceleration as dv dt is equal to F net. So that's for a single particle. And what we want to do is be able to write down what this looks like for a parcel of fluid. And so if you like, it's kind of like dividing both sides by a volume. And what that means is this turns into the density of some fluid. And by fluid, by the way, I mean it could mean gas or water or just a collection of particles, anything that has a sort of more or less contiguous structure, something that would take on the shape of whatever container it was in. This looks like density times dv dt, and then there's sort of F net divided by the volume. And there are two sources of force, if you like, in this problem. One has to do with the fact that we imagine that this fluid has some pressure, and where there are regions of high pressure compared to low pressure, there will be a net force going from high to low. And the way that gets described with a fluid is in terms of minus a gradient of pressure. Okay, so I'll put little vectors on top of my gradient. And this is, in a lot of ways, just like force is minus the gradient of the potential, meaning that you are pushed from regions of high potential to low potential, just like you are pushed, or fluid is pushed from regions of high pressure to low pressure. There's also the term that has to do with Newtonian gravity, and I'm going to write this as minus the density times the gradient in the gravitational potential, phi. I'm not sure if this form is familiar to you, but let me at least write down how phi is related to the density. I'll write grad square phi is equal to 4 pi g rho. You can think of this like you might call this Poisson's equation. Poisson equation. And it really has the same form as Coulomb's law. Del dot E is equal to, rho over epsilon naught, something like that. And E is minus the gradient of the electrostatic potential, but here there is not a minus sign there. Well, at least there's an extra minus sign, perhaps you could say, because gravity is an attractive force. But anyway, that is the relationship. Phi here is the gravitational potential per unit mass. And so when you multiply it by the density of the fluid, that gives you the amount of force per unit volume. So this is force per unit volume, this is force per unit volume, and this is also force per unit volume. So that is what Newton's second law looks like for a fluid. when you only have pressure gradients and gravity to worry about. That's the first equation that we might use. And again, I know this is a crash course in fluids, and so I'm not going to do any more detailed derivation. Poisson equation is also needed, but what I have to indicate is that this Poisson equation will actually be 4 pi g times the overdensity. That's the relevant quantity that goes here. Because there is some background average density, but we imagine that that only contributes some constant value to the potential, if you like. So any derivatives on the potential would the derivatives on the constant term would vanish, is one way I could say it. Yeah. Okay, so those are two equations that we'll need. This is 1 and this is 2. The other one is conservation of mass. I should say local conservation of mass. So these are the two concepts. There's a third concept, local conservation of mass, which basically says, the mass that flows into or out of a particular volume would be related to the total change. So if suppose there's some fluid and you picked a little volume in which to analyze what's going on, and inside of this little volume element, I'll say it as a volume V, then you've got some density. If you think about it, the rate of change of the density in some volume of fluid is equal to minus the rate at which a fluid flows out of this volume. And without deriving this, because we don't quite have enough time, I'm going to write this as minus the, what's this called? It's not the gradient. Divergence. Yeah, it's the divergence. Minus the divergence of a mass flux, and that can be written as the mass density times the velocity. Okay, so remember what divergence does is to measure, it's a vector calculus measure of how much a vector field spreads out. And so if you've got a net amount of fluid that's leaving this volume, then you put a minus sign in front of it, and that tells you about the rate of change of the density within that volume. So I'll just do one more rearrangement then, if you more or less buy this derivation, that rho dot plus the gradient of the quantity rho times velocity, that's equal to 0. This is called the continuity equation, and you've probably actually seen a version of this if you've taken quantum mechanics. So this is continuity equation. And that would be enough to get going. But the additional thing that we want to do is similar to the lecture that appeared before this, which is to do a perturbative analysis. We imagine that there's a background value of pressure and density, and that on average the fluid velocity averages out to 0, and again there's some background value of the gravitational potential, but that is homogeneous. So what do I mean by that? So what I mean is we need to define we need to specify our perturbation theory, our perturbative analysis. And in order to do this, what I'm going to do is the density, whatever the background density is, it has some average value, rho bar. And again, we're on a flat, or a static spacetime rather, so we have an average density in the background that does not depend on position and doesn't depend on time. It's just a constant. And then there's a perturbation to this, which depends on position and time. You can say the same thing for the pressure. It has a background value, doesn't depend on position or time, and then there's a perturbation to that. We also can relate the differences in density and differences in pressure, because you imagine this is some kind of normal fluid, has an equation of state, and so that would mean that the pressure is somehow a function of the density. And the way to think about this is to write, well, the pressure is a function of density, and the pressure therefore is a function of the background density plus some small perturbation. And throughout all of this, and perhaps I should have maybe color-coded things a bit more, I really want you to focus on this delta rho, delta p, so that you can really make it intuitive that these are small quantities. And by that, what I mean is that, delta rho over rho bar is small. Delta p over p bar, These are supposed to be P's. I know that it's annoying that rhos and P's look so damn similar. They are small. Okay, so what that means is we can do a Taylor expansion of this pressure expression. And so what that means is this is approximately the pressure evaluated at the average density plus the derivative of the pressure with respect to the density evaluated at the average density, and then multiplied by the little change in density. Okay, and if you think about it, if you compare this line to this line, that means that this first term, this leading 0th order term, needs to be apparently the average pressure. Now let me just maybe color code this a little bit better. Okay, we've got that. The other thing to do is to note that the speed, whenever you find a velocity, again, the average fluid velocity is 0. We're assuming it's isotropic. But this is small. It's got to be small in some sense. And later on, we'll have to explain what the hell we mean by small. So I'll put that in quotes, right? It has to be compared to some other speed in the problem. And that speed is actually going to be the sound speed. And lastly, let me just note that the potential phi would have some kind of background value plus some little change in the potential. And because it actually doesn't matter where we put the overall potential, we can just let the background value be 0. Okay, we're just setting picking our gauge is a way to say it. And so we'll just let phi is delta phi. In other words, we'll just let phi be a small quantity. So if it's okay with you, let me then just write delta phi so that it's small. So you can identify, these are the small things. Delta rho, delta p, v, and phi. Those are going to be the terms that represent the first order perturbations, and if they ever multiply another small thing that's another first order perturbation, that would give you a second order term in small quantities, and those we will throw away. Have I numbered these equations? We've got a 1 and a 2, and the continuity equation is 3. And so we're ready to make some progress. Let's take a time derivative of the second equation. Is that what I want to do? No, I think I mean taking a time derivative of the third equation, and then we're going to use the first equation in there. So time derivative of the third equation, time derivative of 3, tells you that, well, that rho dot becomes a rho double dot. And when I write rho double dot, I mean, I suppose what I should really be careful of is that rho double dot, get to this in a second, I guess, this is plus the time derivative of the gradient of rho times v equal to 0. And using our first order analysis, what we see is that, remember, rho has in it that first term which doesn't depend on time or space. So what shows up in this equation could only be derivatives on that second term. In other words, this must be delta rho double dot. Likewise, in this equation, your v is, we're treating it to be a small quantity, which means that to this level of analysis, if this equation is only supposed to be trusted to first order, that means that this rho can be replaced with simply rho bar, because that extra term that I could include, the delta rho, would multiply this small quantity v and go away because it's second order. That's good, because that means that I can take this time derivative and send it all the way in. It doesn't act on the rho bar, it only acts on the v. And so when I write this down, apparently what I have, I'm going to try to keep consistent. I've got a delta rho double dot plus the gradient acting on rho, and then a dv dt. I guess I'm getting lazy with my color coding, but I think I'm doing this for a reason. That is to this level of analysis, right? And so perhaps I should put a bar on this, but at least to first order, I think that is okay. That's good, because now if you'll notice rho times dv dt, that's exactly what shows up in that first equation, Newton's second law for fluids. And so I can replace rho dv dt with minus the gradient of pressure minus rho times gradient of phi. So right, this is minus gradient of pressure minus rho times gradient of phi. Now keeping in mind something, that again we're taking this to first order, minus the gradient in pressure. That means that, well, okay, we'll get there in a second, so don't get too excited. Let's clean up what we have. We've got a delta rho. Make this small. Yeah, sure. So we've got a delta rho double dot, and then minus this divergence acting on this gradient gives you Laplacian squared on pressure, and the same thing happens with this one. Again, that derivative, this one here acting on this rho, this is actually just rho bar plus small, and so we're ready to insert that. So what I should put here is minus rho bar gradient squared, or Laplacian, right, acting on phi, and that's all equal to 0. I hope that I'm not going too quickly with this. Okay, let's see. Right, that's what we've got, and what I'm trying to do is massage this until I can turn this into an equation that only has delta rho in it. We're almost there. I'll point out a couple of things. Make sure I separate this so you realize what's here. Gradient squared on phi, that is 4 pi g times rho. In fact, it's 4 pi g times delta rho. Yeah, okay, good. And this term here, the gradient squared in Laplacian on pressure, this is the gradient squared on, well, I can replace the pressure with, scroll back up or rewind if you want, the background value plus the small perturbation, which I've been able to write this as derivative of pressure with respect to rho, evaluated at rho bar, times a little delta rho. Okay? And this Laplacian acting on the background pressure gives you 0 because it doesn't depend on space or time. This term here is also going to be evaluated at some background value. And so what that means is that we're almost at the punchline. We're almost at this pressure wave equation with an extra special term. Delta rho double dot, I'll color code this in a minute, minus, and this term comes out front, dp, in fact, I'm just going to go ahead and tell you the surprise. This is identified as the sound speed squared. The pressure, the derivative of the pressure with respect to the density is the square of the sound speed. So I'll write simply sound speed squared times Laplacian on delta rho, and then over in this third term we apparently have a minus, and I'll write it in this order, 4 pi g rho bar times delta rho. There we go, and I'll just color code it again for you. There's supposed to be some fun thing I could do, wasn't there? Oh, yeah, good. That's a small thing. That's a small thing. That's a small thing. Yeah, good. It's now a linear equation that describes how the overdensities evolve in time. It's got a double time derivative. It's got a gradient term acting on it. If we only worried about the first two equations, that would be a wave equation that you've hopefully seen before. But there's an additional term that is always making the overdensity want to go in a certain direction. That is due to the gravitational attraction. Good. So that's where we are, this pressure density wave. The last thing that I'll do to add in even some more mathematics is to point out that one could do a Fourier transform on this, which is common to do. The Fourier transform, I don't know how many of you have seen, but right, what the basic idea is that you take your position, you go from position space to Fourier space, And for example, what that does is if you have just a simple plane wave in real space, when you transform into Fourier space, and what you get is a function that looks like p, and it's peaked at the wave vector corresponding to this simple plane wave. And if you've got a more complicated wave, then it's more complicated in Fourier space. If you have not seen that, don't worry, I'm sure you will eventually. What happens when you do a Fourier transform? If you've done enough of these, you realize that the Laplacian turns into a minus k squared, where k is simply equal to 2 pi over the wavelength of the waves that you're analyzing. Okay, so what that means in the Fourier transform of this nice equation that I'll box, that means that this turns into, once you Fourier transformed, it turns into delta rho dot and then a plus cs squared k squared times delta rho, and then minus a 4 pi g rho bar delta rho equal to 0. And perhaps you can already see that the sign on the so-called pressure term, the one with the sound speed squared, is positive. The sign on the one with gravity is negative. That means that these two things are having an opposite effect. Let me lastly turn this around, or solve for delta rho dot. So now it'll look even more familiar. I'm going to take these other two terms to the other side and write this as 4 pi g rho bar minus cs squared k squared, and this all multiplies delta rho. And this will hopefully look familiar. It should look a lot like the equation we saw in the last video. And with any luck, this is the kind of equation that you have seen before. Notice that if the term in brackets is greater than 0, like happened when we neglected pressure, when you neglect pressure, right? It's like this term goes to 0, and that would be just like what we had solved the last time. Then what you get is exponential growth. It's one of the solutions. When this term in brackets is less than 0, you get oscillations. And if that's not completely clear, go back to your calculus-based intro physics when you studied the harmonic oscillator and you saw an equation that looked like x double dot was equal to minus k over m x, right? The fact that this term is negative, that tells you that you get oscillation. So there's a difference between whether you get exponential growth of structure or you just get sort of oscillation, a feedback, or a fighting, I guess, between gravity pulling things in and pressure wanting to equalize things, right? So even in the absence of gravity, you could still have things that expand and want to come back in, but gravity's always pushing one way. Pressure is trying to make things go back to equilibrium. But anyway, there is a critical difference that happens when this bracket term transitions from positive to negative or negative to positive. So the critical, I'll just say critical is when the box is equal to 0, and that happens at a special wave vector or wave number k, which corresponds to a special wavelength lambda. That length is called the Jeans length. That separates the difference between structure trying to grow and structure oscillating. So let's just see where that happens. Developing a stutter. 4 pi g rho bar is equal to cs squared k squared. That's when that would occur. I'm going to call this kj, J for jeans. It was probably named after Levi Jeans or something. Who knows? This is equal to cs squared, and that jeans wave number, remember, that's related to 2 pi over lambda, and that's lambda j, the jeans length. That's the relationship there. I'll leave it to you to solve for the jeans length. Lambda j is equal to square root of pi, check my notes, over g rho bar. That is the so-called jeans length. And convince yourself it's true that for wavelengths that are longer than lambda j, so lambdas that are bigger than lambda j, you can get growth. You get your exponential growth. Structure would start to form. For wavelengths that are smaller than lambda j, you get oscillation. So although we were perhaps worried about the atmosphere collapsing or a pool of water collapsing, if you actually determine what is the Jeans length for the atmosphere or for a pool of water, in other words, what is the length above which you'll get gravitational collapse, and below which you'll just get some oscillation. So I'll let you plug in these numbers. Lambda J for air is approximately, I compute this to be 7 times 10 to the 7 meters. In other words, 70 million meters or 70,000 kilometers. So well beyond the size of the Earth. By the way, that's using the speed of sound is equal to 343 meters per second, and the density of air, which is like 1 kilogram per meter cubed. If you do it for water, you're actually not going to get too much of a difference. Although the density of water goes up by a factor of 1,000, it only shows up here in the square root, and on top of that, the I forgot something apparently. There it is. Good. On top of that, the speed of sound in water is significantly higher. So it turns out that if you compute the lambda, the Jeans length for water, you'd find this is approximately, I'll put approximately, 10 to the 7 meters. The speed of sound in air is something like speed of sound in water, I should say, is about 1,500 meters per second. And the density is like 1,000 kilograms per meter cubed. Anyway, that's why a swimming pool doesn't collapse, and why the atmosphere doesn't collapse. The Jeans length is quite large. Anyway, this Jeans length is important because it sets the scale for the growth of structure and oscillations that are imprinted in the universe, such as on the cosmic microwave background and in the large-scale structure that we observe.